So I'm going to be talking about section 15.2 titled Line Integrals. So to evaluate a line integral, let f be continuous in a region containing a smooth curve C. So if C is given by r of t, which is a parameterized function, then the line integral can be found by integrating the parameterized function multiplied by the magnitude of r of t, and it's bounded by values of t. So this can be used for functions of 2 or 3 variables, as you can see. So I'm going to be showing an example when r of t is given, so the path is given to you, and it's already parameterized. So first of all, you're going to, x of t is 4t, and y of t is 3t. So you just find the derivatives of that. So 4 and 3. Okay, and then the bounds are given to you as well, so 0 to 1. So you just put that in there. And so it's x times y, so 4t times 3t, and just the magnitude, which would be 4 squared, so that would be 25 dt. So you're just following the formula. So these are the derivatives added up. 12t squared times 5 dt. So that's 60 t squared. So the derivative of that is 60 over 3, which would be 20 t to the third, evaluated from 0 to 1. So that leaves you with a value of 20. So if you were told to find the line integral for a problem like this, where you're not given the parameterized function, you're just given line segment from one point to another, you would have to find the parameters yourself. So there's a formula for this. So x equals 1 minus t times x1 plus t x2. So this would result in x equals t. And same thing for y. Y equals 1 minus t y1 plus t y2. So that would also equal in y equals t. So now that you have your parameters, you just have to find your bounds. So t goes from 0 to 1, and you have to find your derivative. So x prime t equals 1, y prime t equals 1 as well. So now to just define the line integral, so from 0 to 1, so x squared, so this is the original x squared plus y squared. X is t, y is t, so t squared plus t squared times the derivatives added up, 1 squared plus 1 squared dt. So this would be 2t squared, so that's root 2 dt. Alright, and to find that, so that'd be okay. To evaluate that from 0 to 1, it would result in just 2 root 3 over 3. So that's your final answer. On to line integrals of vector fields. Line integrals can be used to find work done in a force field F. So for an object moving along a path C in the field, at each point consider the projection of the force vector F onto the unit tangent vector T. So the increment of work done on a small subarc is the product of the force and tangent vectors. So it would be force times distance, or F times T. So to find total work done, it can be found by integrating the product of F and T vectors. So this can be translated into other forms that ultimately just mean the same thing. So the most common one in the section that we're using is this one. So for the definition of a line integral of a vector field, so if F is a continuous vector field defined on a smooth curve C given by r of t, which is a parameterized vector, and the bounds are given. The line integral of f on c can be found by basically putting the bounds and integrating f of x t y t z t times r prime t. So in this example, you're told to evaluate the line integral where c is represented by r of t, and the vector field is x of xyi plus xzj plus yzk. So given the curve, so x of t would be represented by t, y of t would be represented by t squared, and z of t would be represented by 2t. So this can be substituted into the vector field. So f of xt, yt, ct would equal t times t squared I plus t times 2tj plus t squared times 2t. Okay. Alright, so that would equal t third I plus 2t squared j plus 2t third. So the next step is to differentiate r of t with respect to t. So r of t was ti plus t squared j plus 2tk. So the derivative of that would be I plus 2tj plus 2k. So now we have everything we need to plug into the line integrals. So we already have the bounds, which are 0 to 1. Okay, and we have our vector field force in terms of t. So that's t third I plus 2t squared j plus 2t third k. That's going to be multiplied by r prime t. Okay, so that would be t third plus 4t third plus 4t third. Okay, so that would equal 9t third dt. So that would be 9 over 4 t fourth, and from 0 to 1, so that would evaluate into 9/4, and that is our final value of the line integral. So in this example, we're going to find the work done by the force field on a particle moving along the given path. So all this information is given to us, and this is the path, and the bounds are also given as well. So we're first going to start off by finding the parameters. So x of t is 2 cosine t, y of t is 2 sine t, and z of t is t. So for the force field, this would be there's just one x value, so 2 cosine ti plus 2 sine tj, and it's minus 5z, and z of t is t, so it would be minus 5t k. So this is our new force field, and now we're going to find the derivative of rt. So that would be negative 2 sine ti plus 2 cosine tj and plus k. Okay, so now we're just going to find the work done with the line interval. So the bounds are 0 to 2 pi. We're going to multiply. Okay, so that's the setup. So the dot product of that would be 2 cosine t times negative 2 sine t would be negative 4 sine t cosine t plus 2 sine t times 2 cosine t, 4 sine t cosine t plus negative 5t times 1, which would be b minus 5t. Okay, as you can see, this cancels itself out. So we're left with negative 5t dt. So to integrate that, we have negative 5 over 2t squared evaluated from 0 to pi. Okay, so that would be 2 pi. 4 pi squared. So that would equal negative 10 pi squared. So that is our work done. That's the final answer. Okay, so just to note, the orientation of C is usually counterclockwise, which makes it positive. But if the orientation is reversed, so the T of T would be negative. And so we would take on this form.